Welcome to the first module of this course, low voltage CMOS circuit operation. So, the first module is regarding description of MOSFET operating in weak and moderate inversion regions. As we have told, the modules are quite independent in nature and can be seen independently. So, the first lecture in this first module is on a review of basic MOSFET operation. So, we will discuss band diagrams in quasi-equilibrium, we will discuss charge distribution, and we will discuss quasi-Fermi level and quasi-Fermi levels, and then we will apply them when your drain to source voltage is not equal to 0. And we will use all this to understand the relationship between electric field in the gate stack and the charges in silicon. So, that will help us understand surface potential, charges, relationships between them. So, we had discussed in the introductory lecture that it is moderate inversion region which is very important, weak inversion and moderate inversion, and also strong inversion in low voltage MOSFET operation. So, now discuss the basic structure of the planar MOSFET. So, here in equilibrium condition when Vg is equal to 0, you would find that there is a usual, because of the work function difference, there is a depletion region. Now, the depletion region here in this part is because of the PN junction, the body to source PN junction, it is because of that. And the depletion region here under the gate is different, that is because of the gate voltage and the resulting electric field in the oxide and silicon. So, how is that happening? Let us see. So, when you apply a gate voltage 0, there could be a work function difference, and because of that work function difference, there would be, to get an equilibrium condition, there would be redistribution of charges and already be a depletion charge here, as you might have seen in a prerequisite course. Now, you increase the gate voltage. Suppose you increase the gate voltage now. So, it is now greater than 0. So, what would happen? Now, if you draw a Gauss cylinder here, so now the depletion region would increase here, and why would it increase? Let us see. If you draw a Gauss cylinder here, and the bottom lid is in the neutral P region, and the top lid is, you could keep it anywhere, you could keep it in the depletion region here, you could keep it in the oxide. So, you can keep it anywhere. Suppose you keep it in the oxide here. So, when you have increased the gate voltage, the charge in this Gauss cylinder would increase. In this Gauss cylinder, what you can observe is that since VDS is 0 and this is a long channel device, you would observe that the electric field fairly in the middle of the channel, then all the horizontal components of electric field would cancel, VDS is 0, and therefore, only the vertical electric field you need to consider. So, in that case, what would be the surface integral of electric field along these vertical surfaces? Vertical surface of the cylinder, it would be 0. Only the surface integral of electric field in this top lid must be considered. In the bottom lid, the surface integral of electric field will come out to be 0, because the electric field itself is 0, it is a neutral P region. So, as you increase the gate voltage, you can see that the charge in the, if the depletion region increases, the charge in the Gauss cylinder would increase. So, if charge in the Gauss cylinder increases, then the electric field seen here, the electric field in the oxide would increase, because the surface integral on the top lid would increase, isn't it? The surface integral of the cylinder for the entire electric field, would be equal to the charge in the cylinder, isn't it, divided by permittivity. So, that is what is the surface integral. Now, however, if for our Gauss cylinder, because the surface integral along these vertical surfaces and the bottom lid is 0, therefore, this would actually turn out to be the integral of surface integral of electric field only in the top lid, and that would come out to be the entire charge in silicon divided by permittivity. So, therefore, as you increase the depletion charge here, you would find that the electric field here increases. So, what would happen? The drop across this oxide would increase because the electric field in the oxide is increasing. It is an ideal oxide we are assuming right now. So, this is how the gate voltage is being supported. Increase in gate voltage is being supported by the increase in depletion charge and the resulting increase in electric field in the oxide. In silicon also, similarly you can see that the electric field increases. Suppose the depletion region increases because of an increase in gate voltage, depletion width increases, then for the lid here, if you keep the Gauss cylinder only from here till here, the electric field would increase here because of the same reason as explained. So, as the gate voltage increases, Vg increases, that would result in a increase in depletion charge, it increases, and that would result in an increase in electric field in silicon oxide, the electric field also increases. So, that is how the increase in gate voltage is being supported. Now, let us look at this equilibrium condition in more detail. So, even in equilibrium condition, when the gate voltage and substrate, that is body voltage, source voltage, drain voltage all 0, we have observed that there is, due to the work function difference between the gate material and p silicon substrate, you would have depletion charges. So, how would you look at that from a band diagram point of view? And before that, how would the electric field or potential change? So, you can see that the potential here chi 1 is within the neutral p region. So, this you can say that it is 0. If that is our 0, then the potential as you get into the depletion region upward, that is in the positive z direction, you would observe that the electric field should keep on increasing, because if you take this Gauss cylinder, then as you move upward from this point, that is where the depletion region begins, you would keep on and you take this lid up and see what is there, how much charge is there within this Gauss cylinder below the lid, top lid. You would observe that it would be the depletion charge would get accounted in it, depletion charge below the lid. Suppose you take this point to be z equal to 0, that is the edge of depletion region, and you take one lid here, okay, and say that this is z, this is point z1, and now you want to see what is the electric field here. So, you would apply Poisson equation or Gauss law, whichever way. So, it would be electric field of that point z would be isn't, where Nb is the doping density. Okay. Now, what is the potential? Let us use chi for potential. What is the potential at Z? Or so to say Z1. I have just integrated electric field so that would give me the potential. Now, what is the direction of electric field? It is negative charges are in silicon and positive charges are in the gate. It is negative actually, right. So, this is how the potential within the depletion region would change as you go upward in the z direction from the bottom edge of the depletion region, that is from the neutral p region, p body towards the gate oxide silicon interface. Now, let us look at this from a band diagram point of view. So, this is in system is in equilibrium. So, source, so the body here and gate material are in equilibrium. So, the Fermi levels would align, that is what is happening. And now, let us see what is this difference. This is intrinsic level and this is Fermi level. So, you have intrinsic level and Fermi level. Okay. So, this let us call it Q phi f, this difference. Okay. And at this point, let us call, let this be our point Z1, this is Q chi of Z1. Okay. So, this is Q chi of Z1. So, how do we relate the electron and hole concentrations with this? So, let us call the electron and hole concentration deep inside silicon, that is in the neutral p body region, as P naught and N naught. So, this is hole and electron concentration. So, what is the value of P naught? P naught you can write as isn't, where you can say that ut is kT by q, thermal voltage. Okay. And how much is N naught? Okay. So, as you move into the depletion region in this direction, as you move in this direction into the depletion region. So, what is the value of P and N? So, let us now distinguish it, let us call it PP. PP is Ni exponential phi f minus chi by ut. So, what is this chi? Chi is the potential here. Suppose you want, and PP of Z1 would correspond to the potential at Z1, isn't? So, you need to replace this with this potential. Okay. That is how you get the hole concentration at point Z1. What about electron concentration at point Z1? So, the electron concentrations at point Z1 is okay. So, again you get NP PP equal to Ni square, because it is in equilibrium. Okay. So, now let us look at this in a way which gives us a better physical idea. Now, let us look at this Ni. So, you can write Ni as you have just inverted this expression and you have just said that Nb, the doping density, is nearly equal to P naught, which is hole concentration deep inside the neutral P region. Okay. So, if you use this, then you can write Pp, that is hole concentration within the depletion region or within the MOSFET channel. So, this depletion, this is called channel of the MOSFET. Okay. The under the gate closer to the silicon dioxide interface within silicon, this is all channel of the MOSFET. So, you could have written this whole concentration within the depletion region as this is coming from here. Likewise, you could have written electron concentration within the depletion region isn't? So, this second thing is quite interesting. So, what you could see with this is that if the surface potential, where is the surface potential? It is here at the interface. The surface the potential, we are calling it surface potential. If the surface potential is 2 phi f, then you get from this expression, you get that electron concentration is equal to Nb. Okay. Now, this is the strong inversion condition as you have discussed earlier. So, when you increase the gate voltage any further, you would get that the potential increases and exponentially Np increases. Okay. So, this is the strong inversion condition which you have discussed earlier. But before the onset of strong inversion also, you can observe that Np could be significant, though it would be smaller than Nb. Or more interestingly, and the electron concentration at the interface or within the depletion region is going to be larger than intrinsic carrier density Ni, in case the potential in the depletion region is larger than phi f. Okay, this is something which we can keep in mind. Okay, so now let us get used to what are the important values here. Suppose Nb is, in our example, Nb is 10 to the power 18 per centimeter cube. What is the value of P naught? Ni, we can take it to be 1.5 at room temperature, 1.5 10 to the power 10. So, what is the value of phi f? You can get phi f from here. Okay. So, phi f is so how much is that? This is so this turns out to be in our example 0.47 volt. Okay. So, what is the value of hole concentration in the depletion region? Suppose you have moved into the depletion region at a point Z1, where suppose chi of Z1, that is potential, is just 0.1 volts. Okay. So, this is smaller than phi f. Okay. Chi of Z1 is now smaller than phi f. So, you have moved just into the depletion region. So, in that case, what is the value of hole concentration here? So, that is 1.5 into 10 to the power 10, which is Ni exponential phi f, which is 0.47 volts, minus 0.1 volts divided by 0.026, which is thermal potential, thermal voltage. So, this turns out to be nearly 10 to the power 16 per centimeter. So, you can see that as you move slightly into the depletion region, there is a 2 orders of magnitude reduction in the hole concentration. What about electron concentration? Let us see the electron concentration. So, electron concentration deep inside silicon, that is in the neutral region, you can see from here, it is intrinsic concentration Ni, this comes out to be some 210 or 211 per centimeter cube. Okay. But what is the electron concentration in the depletion region for Z1 or for chi equal to 0.1 volts, that is potential 0.1 volts. So, this would be so this would come out to be nearly 10 to the power 4 per centimeter cube. So, you can see that as you move from the neutral region slightly into the depletion region, you find that there is a 2 orders of magnitude increase in the electron concentration. So, this is something which we can keep in mind, that the electron and hole concentration change exponentially and very rapidly as you move into the depletion region from the neutral body. There is a drop in the oxide also, that is because of this, as we had discussed with a vertical Gauss cylinder from the gate to the silicon body. So, as we had discussed, then you can see that there is a charge in the Gauss cylinder, and therefore, there is electric field in the oxide, and that electric field would result in band bending in the oxide, and the band bending is straight because we are assuming ideal oxide and there is no addition of any charge in the oxide. Now, let us discuss the MOSFET operation when the gate voltage is now increased from 0. So, once the gate voltage is increased from 0, it is the device is no longer in equilibrium. So, because there is an exchange of charges and energy, you are not keeping it in equilibrium. So, what would happen now? Because there can be no VDS, we are keeping 0. So, there is no current. So, and because there can be no movement of electrons or holes across this oxide, that we are assuming it to be an ideal oxide. So, there is no current anywhere. So, if there is no current anywhere, electron current, for example, is proportional to electron concentration and the Fermi level. Now, this Fn is quasi Fermi level. We will discuss quasi Fermi levels as we go ahead, but right now, so we will discuss quasi Fermi levels as we go ahead. So, the current density is 0, electron concentration is not 0. So, Fn is constant and it does not change. So, though the device is not in equilibrium, hole and electron quasi Fermi levels would match and they would stay constant throughout the silicon, because the current densities are all 0, because VDS is 0 and there is an oxide between the gate and silicon body. So, therefore, the quasi Fermi levels would all be constant, and the quasi Fermi level deep inside silicon, that is in the neutral region, it is the same as similar to the equilibrium condition in the neutral region, and that is why there is a charge neutrality. If there is charge neutrality, then the dopant ions concentration, their concentration might be is getting balanced by carrier concentration. It is the carrier concentrations are like what you had in equilibrium condition. So, therefore, the quasi Fermi levels would also match with the equilibrium Fermi level deep inside silicon, here. But we have observed that since the current densities are all 0, the quasi Fermi levels need to be would be constant, and therefore, they would be constant throughout, that is even within the depletion region. Now, let us calculate a a few things here. So, what is the value of electron concentration at the interface? So, electron concentration at the interface, if you keep on increasing the gate voltage, you would find that the electron concentration at the interface so that would become so if you keep on increasing the gate voltage, this would turn out to be NB as we had discussed earlier. So, what are you doing? You are increasing the gate voltage. So, therefore, silicon body, the neutral body, it would have same concentration. So, as it is, this entire bands would move upward, so to say, and since they are moving upwards, there is a can depict it as a larger band bending here, and so that would result in a larger value of chi s. So, when you keep on increasing the gate voltage, the depletion charge here builds up, there is a larger depletion charge, and therefore, the surface potential would increase, because in the Gauss cylinder that we had discussed, you would find a larger amount of charge. This is the depletion charge. So, you would find a larger amount of depletion charge, and therefore, the surface potential would keep on increasing, isn't? So, if the surface potential is larger than 2 phi f, that is where 2 phi f, we had seen that NP would be larger than NB. So, after this, what would be the hole concentration? The hole or the electron concentration here would be equal to NB, and hole concentration would be quite small, it would be equal to Ni. Now, you increase the value of gate voltage. What would happen? If you further increase the value of gate voltage, so now the electron concentration would look like so the electron concentration would increase exponentially with further increase in surface potential. But let us now along this Gauss cylinder, let us write a relation for the gate potential. So, what would it be? Gate potential would be potential across the oxide plus the surface potential. Okay. Now, what is that? Potential, and you have to correct it with the flat band voltage. Flat band voltage is the correction because of work function differences. So, this would turn out to be where Q silicon is the total charge in silicon. This is the oxide. This is the oxide potential drop. So, what is this? So, Cox is the oxide capacitance per unit area. So, now as you increase chi s about more than 2 phi f, suppose chi s is greater than 2 phi f, then you keep on exponentially increasing, as you can see here, you exponentially, because this is larger than this is the expression now. So, you keep on exponentially increasing NP. So, if you exponentially increase NP, silicon charge exponentially increases, and that results in a, so if you increase Vg gate voltage by a certain value, you increase the surface potential by a small value, silicon charge would increase exponentially, and therefore, the surface potential needs to increase by only a very small value after the onset of strong inversion. So, we will now discuss what would happen if the drain voltage also is non-zero. Yeah, before that we will discuss the band diagram along this line B B prime. This B B prime is located at the gate oxide silicon interface within silicon, but just at the interface. So, when the gate voltage is 0, this is the band diagram. Okay, this is conduction band, valence band. Okay. Now, you increase the gate voltage. So, once you increase the gate voltage, the depletion charge here builds up, and along A prime line, you would find that the band, the conduction band was like this. Now, it has, if you align the conduction bands, then it would look like this. They are not aligned, actually it will, but just for the sake of understanding and comparing, we are aligning. So, now this is the conduction band with an increased gate voltage. So, you have increased the gate voltage and the band bending has increased along the A prime line. So, now this is along A prime line. So, and what is the corresponding picture along B prime line? It is this. This is the corresponding picture. So, in the gate, you would observe that the conduction band has moved down the electron potential. Conventional potential has increased. Okay. Likewise, you increase the gate voltage further, the conduction band will move further down. So, as you keep on increasing the gate voltage, the conduction bands now aligns with, almost aligns with the conduction band of the source and drain. So, once it quite aligns with the conduction band of source, now electrons in source have a thermal energy. So, that thermal energy, if it is, if the difference between the conduction bands in source and in the channel is comparable to the thermal energy, then you have injection of electrons from source into the channel. So, that is why when we say that surface potential is larger than 2 phi f, the electron concentration now increases exponentially with surface potential, and actually the surface potential, actually as we had seen that the surface potential does not increase much, because as you can see from this relationship, so this Q silicon is composed of inversion charge plus depletion charge, and this inversion charge, as you had seen, is proportional to so as you increase the surface potential, inversion charge exponentially increases, then a small increase in gate voltage would happen because of a very small increase in surface potential, because now this is exponentially increasing. So, when you have surface potential larger than 2 phi f, suppose it is this case, then as you increase the gate voltage any further, there is almost no increase in the surface potential, because that increase in gate voltage would be supported by a very small increase in surface potential. And because the difference between the band energy conduction bands of source and channel is now quite small, there would be thermal injection of electrons from the source into the channel, and therefore, this is what happens in the strong inversion condition. Otherwise, you would have a larger difference between the source and channel conduction bands, and there would be the thermionic injection of, or thermionic injection of electrons from source into the channel would be much smaller, because few carriers would have that energy. So, we would continue with VDS is not equal to 0 in the next lecture, that is the quasi-equilibrium condition is also not there. So, it is a non-equilibrium steady state condition, which we will discuss in the next lecture. So, in this lecture, we have discussed the basics of MOSFET, carrier concentrations and depletion charges, and also the electric field within in different regions, electric field and potentials in different regions of the MOSFET, and for equilibrium and quasi-equilibrium condition, that is VDS is equal to 0. And we discuss the band diagrams and strong inversion, how it sets in and how the surface potential does not change much. I mean, it changes very little, almost insignificantly after the onset of strong inversion. Thank you.